Hey everyone, welcome back to my channel. This is Dr. Spinach. If you recall, we have already discussed about all the parameters of pharmacokinetics. These include absorption, distribution, metabolism, and excretion. Now, under excretion, an important topic that decides the drug dosage is order of elimination kinetics. Knowledge of kinetics of elimination of a drug provides the basis for rational dosage regimen. That means what dose of a drug should be prescribed at what intervals of a time, and to modify them according to individual needs.
So, what does the term order of elimination kinetics mean?
Now listen to me carefully. Elimination kinetics means rate of elimination of a drug, which is usually taken in relationship with concentration of drug in plasma. And the order tells us the relationship between the two. Let me explain this through a graphic diagram. Let's take the concentration of a drug in plasma at 1000 milligrams. So, how much of this drug is cleared in 1 minute will tell us what is the rate of elimination. Let's say 10 milligram of this drug clears from various routes of elimination in 1 minute. So the rate of elimination for this drug equals to 10 milligram per minute. And order tells us how is this rate related with the concentration of the drug in plasma. Fortunately enough, almost all the drugs in pharmacokinetics follow either zero order or first order kinetics. In zero order kinetics, the amount of the drug eliminated per unit time remains constant, while in the first order kinetics, the fraction or the percentage of the drug eliminated per unit time remains constant. An example of a drug that follows zero order kinetics is Warfarin, which is an anticoagulant. Let's draw a graph on its rate of elimination. Look at this graph carefully. On the x-axis, we have time in hours, and on the y-axis, we have plasma concentration in milligrams. 6 milligrams of the drug is present in the plasma in the first hour, 5 milligram in the second hour, 4 milligrams in the third hour, 3 milligrams in the fourth hour, and so on. Now, let's look at the graph of the first order kinetics. Similar to zero order kinetics, in the first hour, 6 milligram of the drug is present in the plasma. In the second hour, 3 milligrams of the drug is present. In the third hour, 1.5 milligrams of the drug is present in the plasma. In the fourth hour, it becomes 0.75 and so on. Let us write them down again to better understand and remember them. Starting with the zero order kinetics. In the first hour, the drug reduces from 6 milligrams to 5 milligrams, from 5 milligrams to 4 milligrams in the second hour, and from 4 milligrams to 3 milligrams in the third hour, and so on. Whereas in the first order kinetics, the metabolism looks something like this. The values in red depicts the plasma concentration of the drug with time. It is clear from the figures of the first order kinetics that 50% of the drug is eliminated every hour, while the values of the zero order kinetics tells us that 1 milligram of the drug is eliminated every hour. Henceforth, we can say that same amount of the drug is eliminated per unit time in case of zero order kinetics, and same percentage or fraction of the drug in case of first order kinetics. So, rate of drug elimination in the first case is 1 milligram per hour at every step. It means it does not depend upon plasma concentration. Looking at the second case, 3 milligrams of the drug is eliminated in the first hour. 1.5 milligrams of the drug is eliminated in the second hour, and 0.75 milligrams in the third hour. As is evident in this flow diagram that when plasma concentration of a drug is lower, the rate of drug elimination is also low, whereas when the plasma concentration of a drug is higher, the rate of drug elimination is also higher. Therefore, rate of drug elimination in the first order kinetics is directly proportional to the plasma concentration of that drug. In contrast, in the zero order kinetics, the rate of drug elimination is constant. Let's talk about a few more parameters here. The next one is T-half. T-half is the time taken for plasma concentration of a drug to reduce to half from its original value. Looking at the graph of zero-order kinetics, the plasma concentration of a drug in the first hour is 6 milligrams, half of which is 3 milligrams. So, the time taken for plasma concentration to reduce from 6 milligrams to 3 milligrams is T-half, which is 3 hours in this case. Similarly, the time taken by the drug to reduce from 3 milligrams to 1.5 milligrams is 1.5 hours, which is the next T-half. Looking at the relationship between T-half and plasma concentration, when the plasma concentration is lower, T-half is also lower. And when the plasma concentration is higher, T-half is also higher. So, we can say that T-half in case of zero-order kinetics is directly proportional to plasma concentration of the drug. Looking at the graph of first-order kinetics, the time taken for plasma concentration of the drug to reduce from 6 milligrams to 3 milligrams is 1 hour, and from 3 milligrams to 1.5 milligrams is 1 hour. Then from 1.5 to 0.75 is 1 hour. Therefore, we can conclude that the T-half in this case does not depend upon the plasma concentration of a drug. The last parameter I'd like to talk about is clearance. I have already discussed about the definition of clearance in my last tutorial on pharmacokinetics of elimination. However, let's review briefly here.
So, what is clearance?
Clearance tells us how much plasma in milliliters is cleared of the drug in per unit time, the unit of which is milliliters per minute. The formula for clearance is rate of drug elimination divided by plasma concentration of a drug. So, rate of drug elimination in the zero-order kinetics is 1 milligram per hour, and the plasma concentration of a drug is 6 milligrams. So, the clearance becomes 1 by 6, that is 0.15. In the next hour, rate of drug elimination is 1 milligrams and the plasma concentration is 5, which equals to 0.20 as clearance. The next one, it is 1 by 4. That means 0.25, and so on. As you can see that as the plasma concentration of a drug decreases, the clearance of the drug increases. Therefore, we can conclude that clearance in case of zero-order kinetics is inversely proportional to plasma concentration of a drug. Looking at the first order kinetics, rate of drug elimination in the first step is 3 milligrams and plasma concentration is 6. So the clearance becomes 3 by 6, and the next one it is 1.5 by 3, and the next one it becomes 0.75 by 1.5. In all these cases, the clearance comes out to be 50%. Therefore, we can say that clearance in case of first-order kinetics does not depend upon the plasma concentration of a drug. Hey kid, can you rapidly review what we just read?
Yes, Dr. Spinach. We just read 2 types of orders that are followed by almost all drugs during their elimination.
These are zero order and first order. In case of zero order kinetics, the amount of the drug eliminated remains constant. In case of first order, the percentage remains constant. Then we talked about how rate of drug elimination in either orders is affected by plasma concentration of the drug. In case of zero-order kinetics, it was constant, and in case of first-order kinetics, it was directly proportional to the plasma concentration. However, half-life of a drug showed the opposite trend. The volume of the plasma cleared per minute of the drug remained constant in case of first-order kinetics, while it was inversely proportional in case of zero-order kinetics. The parameters we read just now helps the clinician in determining the dosage of a drug. But for that, we need to know which drug follows which type of order. Remember, almost all the drugs follow first-order kinetics. Only a very few, which are going to be soon listed here, follow zero order. These include warfarin and heparin, which are anticoagulants, alcohol, aspirin, which is an NSAID, tolbutamide, which is an oral anti-hyperglycemic drug used in diabetes mellitus, theophylline, which is used in the treatment of COPD and asthma, phenytoin, which is an anti-epileptic. The last but very interesting question you might ask is,
Why do some drugs follow zero order while others follow first order kinetics?
Find the answer to this question and let me know in the comment section below. And if you enjoyed watching this video, give it a thumbs up, subscribe and share. Do press on the notification icon down below to get my latest updates on YouTube. Till then, keep safe and eat healthy diet. Thank you for watching.